Oh, kind of strange colors here. Oh, there we go. So this is eye behavior being recorded from one of my kind volunteers during a rather long and boring scan session. And you may know that even though it's very loud in scanner, it's very easy to become drowsy and even fall asleep, even when the instructions, like in this case, were to maintain fixation. So I'm going to use the term vigilance to describe these fluctuations in wakefulness or brain arousal. And most of the time, we actually have no idea whether or when this is going on in our studies because we don't usually record these kinds of videos or measures like EEG. But this is really important because we know that both behavior as well as the characteristics of neural activity change as a function of vigilance state. And so looking at a couple examples in fMRI data, there are changes in correlation within and between networks as a function of different sleep stages. And even in the more wakeful state, if we look at what happens when people transition from alertness to more drowsiness and potentially light sleep. One of the effects that's been pointed out is that the fMRI signal variance increases quite a bit, as can global correlations across the brain. And so this illustrates that vigilance can really impact the features that we're measuring in our data, like correlations over time or power spectra, and we'd really want to be able to account for this in order to understand our data and achieve greater reliability, and especially as we want to move toward looking at the levels of individual subjects. But this is something that's still not routinely accounted for, and as I mentioned, in part this is because it's not always feasible to gather EEG or eye monitoring during our scans, and especially with certain populations or patient groups that can make it even harder. And therefore, it would be very valuable to have data-driven techniques that could allow us to try and infer vigilance changes from the fMRI data itself. And so there's been some previous work on this. For example, these two studies focused on detecting sleep stages using windowed correlations in the fMRI data. And in this recent study, we looked more at the wakeful state, at continuous variations in alertness and drowsiness, perhaps like the kinds of changes you're seeing in that eye movie. And we asked if we can estimate a time course of vigilance across the scan using only the fMRI data itself and on a TR by TR basis. And so this was developed in using data from macaque monkeys, and when we compared our estimate to independent measures of vigilance like electrophysiology or spontaneous eye opening and closing, we found that there was a pretty good agreement. So to describe a little more how this approach works, the basic idea is to first obtain what we call this template map, and this is basically a spatial pattern that reflects areas that increase or decrease their relative signal levels as a function of vigilance. And the way we can get this is from a set of training data where we've actually recorded some measure of vigilance like EEG, and we can take the time course of that measured vigilance and correlate it with each voxel's time course to obtain this map. And so this pattern you see here kind of indicates that increases in vigilance are associated with increases in the relative signal levels of areas, including the thalamus, but widespread decreases across much of the cortex. So this part is essentially like a training phase, and now if we want to go and apply it to another data set, suppose you have another independent set of data that does not have vigilance measures, one thing we could do is to take this template map and do a spatial correlation on a time frame by time frame basis. That will result in a time course that here we're going to take to be this estimated vigilance level. And so the core of this method here is really this pattern, this template map, and fortunately we found that in our monkeys it was very consistent between one monkey and the other, so we could actually use the template pattern derived from one monkey in order to pretty well predict the estimated vigilance level in the other monkeys. And it's also very consistent with literature in human subjects, and so you can see that there's a similar constellation of patterns where vigilance has a correlation with, is widely inversely correlated with much of the cortex and positively correlated in focal, like subcortical regions. And the color map is just inverted because these are correlates of decreasing rather than increasing vigilance. And so it suggests that there may be a reliable signature of vigilance in both macaques and humans. And so coming to the present work, the question we wanted to ask is whether these data-driven estimates may, and to some degree, account for variability in the behavior on a task in human subjects. And so we're going to focus specifically on a working memory task. We used two separate data sets in the study, one for deriving the template and the other one for looking at the relationship with behavior. And in the first group, we had simultaneously recorded EEG and fMRI. This is all during eyes closed resting state. And in the second group, we had one back task. This was a continuous task over 12 minutes with a fairly short interstimulus interval. We excluded one subject because they had extremely constant reaction times across the scan, and both of these were done at 3T, though with different sequences, and at different scanning sites, so it's kind of an extra challenge for whether or not this would work out and would generalize. Common preprocessing was applied to both of these data sets, including reduction of physiological effects and spatial registration to a standard MNI template. And so within the framework of that vigilance estimation, these two groups were used to basically train and examine the model. So in this data, since we had EEG, our vigilance time course was based on the ratio of alpha to theta power for each TR, and we correlated that with the fMRI data, and we obtained this statistical map across the group where we see that it's really consistent with previous literature. And then we take this and apply it to data from the working memory task to examine the vigilance time courses in those scans, and then compare that to the ongoing behavior, the reaction times. And so this is just some results from the behavioral data. So this is a one back task, so people do pretty well. And if the first thing we tried in order to relate the behavior to vigilance is to basically, for each subject, you can identify trials that are in the slowest or fastest 5% of their reaction times, so kind of extreme trials. And then we can look at the estimated vigilance in each of these sets of trials and see whether there's a relationship. And so that result is represented here. So each pair of dots connected by a line represents a subject, and the blue dots are the estimated vigilance associated with slow trials, and the pink dots with fast trials. And so it was encouraging that we at least get the direction that we expect for most of the subjects. So to make this plot, I actually needed to choose some window around the trial in order to associate it with some vigilance level. And here I had chosen a 2.5 to 5 second post-trial interval to look at that, which if we account for approximately 5-second hemodynamic delay is about a 2.5 second pre-trial interval. But then we want to check, how sensitive is this result to the actual window that we're looking around a given trial, and that's represented here. So these dots are basically the difference between the fast and slow trials in terms of their estimated vigilance, so we kind of want them above the zero line. And this is just as a function of the window around a trial at which we're looking. So this maximum at 3 to 7 seconds is, if we think about hemodynamic delay, is approximately centered on the trial. And so this was for 4-second windows, and we just checked for another window size, 12 seconds. Another question we can ask is, instead of just looking at these isolated trials, what about a more kind of continuous variation in reaction time across the scan? How would that relate to our kind of slow fluctuations in estimated vigilance? And this is an example from one subject where I took a reaction time course and just convolved it with an HRF so we don't have to mentally calculate any time delays here. And in red is the estimated vigilance level. And so maybe some features we're interested in are, for example, if there's a high value here, that's a very slow reaction time. And so we can look and see if there's maybe a pre-trial low vigilance level, which you can see here and maybe over here. And we can also kind of take a cross-correlation over these two waveforms, where we'd generally expect maybe a negative relationship because of low vigilance being related to longer reaction times. And when we looked across our population, we do see a negative correlation, rather moderate. But one question to ask here is, would we really expect, how much of the reaction time variability might actually be driven by vigilance fluctuations? There's, as we know, a number of other factors that could impact reaction time variability, including, mind wandering and attentional effects. So finally, we can ask questions about how does the time course of our estimated vigilance compared to other brain signals or networks in the data in terms of the relationship with reaction time. And so one feature we might be interested in particular is the global signal or whole brain average signal, because as you might remember from this template maps, vigilance tends to be negatively correlated with a lot of the cortex, and in general shows a negative correlation with the global signal. And so we just looked at some of these similar measures in terms of the difference between slow and fast reaction times for the vigilance level and for global signal, which also shows a relationship, though in this case to a lesser extent. We can also look at a bunch of things about the network signals or areas, and this is an interesting area that I'm still exploring, and I wanted to show you one of the results that had rather large effects. So this is the salience network, Insula and ACC, and one thing I found is if I take the cross correlation with the salience network signal and the reaction time course, you get a rather reliable positive correlation. Perhaps this relates to low or very slow or performance lapses being sort of a salient event that relates to higher activation in this network, but we're further investigating that. So to conclude, we find an association between this data-driven estimate of vigilance and a working memory task performance. I should point out that this is not intended to be a rigorous validation of that method for a number of reasons here. One is that factors other than vigilance may impact someone's behavior. And another is because we didn't actually have independent measures of vigilance during that working memory task, which would have been ideal for a more rigorous validation. But we're currently working on that, so we're collecting new data sets that have a different tasks as well as these vigilance measures. We're also looking at improving the method for vigilance estimation. There's a lot we can do there. This is just a simple kind of linear correlation approach. And as I mentioned, there's further work with studying the relationship between vigilance and intrinsic network activity. And I'm really excited about this area in general because I think that this could be very useful for helping to improve the reliability of fMRI data and for actually also using vigilance as a marker of interest, perhaps in brain disorders, especially ones where we know that there is some deviation in vigilance or autonomic processes. So thanks a lot for your attention, and I'd like to acknowledge my colleagues.
The floor is open for questions.
Great talk. Can you say anything about the frequency or properties of the vigilance when you're using the template fitting? For instance, when you found the TRs, were there a maximum number of TRs that would fit the template or a minimum? Did subjects have certain frequency profiles going in and out? Like, can you inform some properties of vigilance from this type of fitting?
Yeah, okay, so in terms of those vigilance estimates, they tend to be pretty low frequency, and if you actually look at the, if you look at the correlation between, or as I showed in the beginning, there was this picture where as people are becoming more drowsy, you see this larger amplitude, low frequency modulation. That tends to be around 0.01 to 0.05 hertz, so it's pretty low frequency. So actually, looking at the frequency of vigilance modulation may be an interesting feature that would be really interesting to see how much that differs across individuals or populations.
Go ahead.
Very lovely work, and so people who study autonomous nervous system have found that vigilance correlate with the heart rate variability. Have you tried looking for that and maybe taking that as an independent measure as a vigilance, and then compare with your method?
Yeah, absolutely. So actually one of the ways that we're extending this is to incorporate information from physiological variables like heart rate and respiration, which can be really predictive of vigilance. And here there was a correlation. Actually should look at that in more detail, so thanks for reminding me, with the heart rate. And if I regressed heart rate related variance from my data, actually got worse predictive power with this method. So there's definitely information there. Thanks.
Okay, thank you for the speakers for very terrific sessions this afternoon, and I'm sure you have many more questions. Please feel to visit the speakers at their posters tomorrow. It's a poster session between 12:45 and 2:45. So let's give a big round of applause to all the speakers.